If you are running a Linux kernel released anytime after 2017, your system is vulnerable to a local privilege escalation exploit that fits in just 732 bytes of Python code. It's called DirtyClone, and it's a critical vulnerability that allows any unprivileged local user to gain full root access to your machine by silently poisoning cached system memory. This isn't a theoretical lab experiment. Security researchers at JFrog have published a working proof of concept, and it bypasses traditional file integrity monitoring tools completely. Whether you're managing enterprise servers, daily driving a Linux desktop, or running containerized workloads, this affects you. Today, we're going to break down exactly how DirtyClone manipulates the Linux copy-on-write mechanism, why it's so dangerous, and most importantly, how to check your system and apply the patch before someone else uses this against you. Let's dive into the technical details and see how this exploit works. Let's get into it. To understand why DirtyClone is so effective, we first need to understand a core concept in the Linux kernel called copy-on-write, or COW for short. Normally, when multiple processes need to read the same data, the kernel is smart. Instead of copying that data into memory multiple times and wasting RAM, it just points all those processes to the same shared memory page. But what happens if one of those processes needs to modify the data? That's where copy-on-write comes in. The moment a process tries to write to that shared memory, the kernel intercepts the action, makes a private copy of the page just for that process, and lets it modify the copy. The original data stays perfectly safe. It's a brilliant system for efficiency. But DirtyClone, officially tracked as CVE-2026-43503, finds a flaw in how the kernel handles this when dealing with network packets. Specifically, cloned socket buffers, or SK buffs. The vulnerability exists in the shared frag handling of these network buffers. An attacker can create a situation where a file-backed memory page, like the memory holding the /bin/su executable, is linked to a cloned network packet. Because of a race condition in the kernel's memory management, the attacker can force a write operation that bypasses the copy-on-write mechanism. Instead of making a safe private copy, the kernel allows the attacker to write directly into the shared memory page. This means an unprivileged user can overwrite the memory of critical root-owned executables while they are running. When another user, or the system itself, executes that file, it runs the attacker's malicious code with full root privileges. Now you might be thinking, wait, if a user modifies a critical system binary like /bin/su, won't my file integrity monitoring tools catch it? Normally, yes. Tools like AIDE or Tripwire are designed to detect when a file on disk has been tampered with. But this is what makes DirtyClone incredibly dangerous. DirtyClone does not modify the file on your hard drive. It corrupts the file-back memory in the Linux page cache. The actual file on disk remains completely untouched, and its hash signature doesn't change. Because the exploit happens entirely in memory, traditional file integrity scanners will look at the disk, see that everything matches, and report that the system is secure. Meanwhile, the attacker has already gained a root shell. This stealth factor is why the JFrog security researchers who published the proof of concept emphasized the severity of this flaw. It leaves almost no trace on the file system, making post-incident forensics significantly harder. If you are relying solely on disk-based integrity checks, you are flying blind against this exploit. Engagement candidate. Deep dive into memory forensics versus disk forensics. Let me know in the comments if you want a dedicated video on this. By the way, I just checked our channel analytics, and it turns out about 82% of you watching right now aren't subscribed yet. If you've been getting value from these Linux security deep dives, hitting that subscribe button is the best free way to support the channel and make sure you never miss the next critical update. So, who is actually vulnerable to DirtyClone? The short answer is almost everyone who hasn't patched in the last few days. The vulnerability exists in code that has been part of the Linux kernel since 2017. This means that virtually every major distribution, whether it's Debian, Ubuntu, Fedora, Arch, or enterprise Linux variants, is susceptible if it's running a kernel released before the patch was merged. The good news is that the kernel maintainers moved quickly once the flaw was responsibly disclosed. As of right now, rolling release distributions like Arch Linux and OpenSUSE Tumbleweed have already pushed patched kernels to their stable repositories. Fedora has also released an update. However, for stable release distributions like Debian and Ubuntu, the patches are currently rolling out through their security update channels. Depending on your update schedule and which specific kernel version you are pinned to, your servers might still be exposed. The only way to be absolutely sure is to check your current kernel version and compare it against your distribution's security advisories for CVE-2026-43503. Let's get practical. How do you secure your system right now? First, identify your running kernel. Open your terminal and run uname r. This tells you exactly what is currently loaded in memory. Next, you need to pull the latest security updates. If you're on Debian or Ubuntu, run your standard apt update and upgrade your kernel packages. For Fedora or RHEL-based systems, use DNF upgrade security to pull in the patched kernel. And for Arch users, a full system sync with pacman-syu will grab the latest 7.0 series kernel, which includes the fix. But here is the critical step that many sysadmins forget. Updating the package on disk does nothing to fix the vulnerability currently running in your system's RAM. Because DirtyClone exploits a flaw in the active memory management subsystem, you absolutely must reboot your machine to load the patched kernel into memory. The only exception is if you are using a live patching service like Canonical Live Patch or Kernel Care, which can inject the fix directly into the running kernel without a reboot. But if you aren't paying for one of those services, schedule a maintenance window and restart your servers immediately. This is not a vulnerability you can afford to sit on. The proof of concept is public, it's trivial to execute, and it grants instant root access. If you found this breakdown helpful, make sure to leave a like and subscribe to the channel. And if you want to support the channel directly and get some cool perks, consider clicking the join button below to become a sudo user or get root access. Stay safe out there, patch your kernels, and I'll see you in the next one.